All right, so can you hear me? Thank you for coming. So today we're very happy to have Ilias Zadik from Yale. So I've known Ilias for many years, since the time that he was beginning graduate student at MIT, and I've liked his work and the way that he does research since then. So Ilias has very broad interests, but like if you wanted to describe his research in one sentence, basically he's trying to understand what are the trade-offs between computation and sort of statistical accuracy for various learning problems and optimization problems. And today he's going to tell us about MCMC and its application to sparse estimation.
Turn this on. Thank you very much, Ilias, and thank you very much, everyone. It's my great pleasure to be here. It's a really long room, so if you have some, I will probably spot some of you, but if you have any questions, just yell at me. Okay. Yeah. Okay. So this is right. So I will be having some slides. Sometimes I will be using the board, which is complicated with such a long room. But I will try my best to minimize the use of the board. But there will be a little bit of board. Okay. Right. So what is this going to be about? So this is one of the topics actually I care about a lot over the last few years, which is trying to understand how Markov chains perform. Okay, I mean, again, if I say something that you don't understand, please ask me. I mean, I understand it's a diverse background. So I will continue. So I will understand how Markov chains perform, or specifically Markov Chain Monte Carlo algorithms perform in what's known as sparse estimation. And I will do this from a mathematical standpoint. So this will be a theoretical talk. Okay, and this is joint work. So actually, most of this work is based on joint work with Zhong Chen, who's a professor at Georgia Tech, and Connor Sheehan, who's a great student at Yale. And time permitted, I'm going to actually discuss also about some recent work with Connor and Max Lovick and Kostas Tsirkas, which are other great students at Yale as well. Okay, so now let's start making things concrete. So, okay, I really need to get this out of here. So let's see. Okay. So the topic is going to be parametric estimation. So, let's explain to everyone what's parametric estimation. So it's a very standard statistical setting. It's the Bayesian one. So what's happening here is there exists some parameter theta star. Okay, so that's the goal. There is some parameter theta star that you want to estimate. You don't know theta star, and you want to learn theta star. And it's sample. What's the assumption here? It's sample from some distribution. So you do know the distribution. That's called prior distribution in statistics. And this distribution is supported on some parameter space theta. And you want to learn this parameter. And the observation you have for this parameter is coming in a probabilistic way, is some data set that is sampled from some probability distribution indexed by this parameter. Make sense, the logic? So you know the prior, you know the observations, you want to find theta star. And to simplify things, I mean, in this talk, I will assume it's a discrete value. Okay, so it takes discrete values. Okay, let's say the goal again. The goal now is to use this data set and give me some guarantee, give me some algorithm that will find this parameter with probability, let's say, at least 0.9. That's based on parametric estimation with exact recovery guarantees.
So the exact,
go for it, yeah.
The exact recovery requirement, you can do this because it's discrete value.
Amazing, yeah. So I want to simplify things. Most of these things just generalize, naturally continuous parameter, mean square error guarantees, but let's keep this simple. Okay. Right. So now, where is sparsity that I mentioned coming in? I mean, let me specify something. We're talking about high-dimensional problems here. And when I say parameter, it's actually not one parameter, a single number. Usually, it's like a long vector, for example. So the parameter, in particular here, for me, it will be something like a very long high-dimensional vector that it's sparse. What's two such canonical priors? It's what's known as the Bernoulli sparse prior, which is basically a uniform random vector chosen from, let's say, for simplicity, like 0, 1 entries in p dimension, and p is large, and only k of them are non-zero. That's a very classical sparse prior assumption. Or it could be, you can go a little bit more complicated. You can assume a Rademacher prior, right? So it means you have k non-zero entries, and which are -1 or 1, and the rest are 0. Okay, so if I say parameter, I mean usually something much more complicated, right? It could be arbitrary things. Okay, let's come back to the general setting. So if you have this general setting, what's the good news? The good news is that we know for many decades now that this is a solved problem. So the optimal algorithm for this problem is known the maximum a posteriori estimator. Oh, this again, okay. So it's called the maximum posteriori estimator. So there's a single optimization problem that's the best algorithm. So what does this mean? Is if you have any algorithm that can achieve guarantee 0.9 probability of exact recovery, then this algorithm also works. And what is this super nice algorithm? It's perhaps the most logical thing you can imagine. It's the one that takes the maximum among all potential values of theta star, the probability that theta star is equal to theta given the dataset. So, the maximum chance that this was the correct theta star given the dataset, the maximum posteriori estimator is the best algorithm. Okay, is this clear? I'm going through background stuff here, but yeah.
Do you also consider cases where just the expected number is k, because then maybe things decouple a little more easily, and then you can do it?
It's absolutely true. So, like here, in this slide, you can consider anything you want, right? But this is just two examples. Okay, you will see, what I'm going through it. I'm just going through basically background stuff to make sure everybody understands the basics. Yeah.
Translate with the scientists.
Yeah.
Basically, what you're saying is that we don't care about computation. We just care about the algorithm that has the optimal sample size or the optimal rate of convergence. If you can solve that optimization problem, then you're done.
Yeah, and I'm saying this perhaps in an extreme form, in the sense that, if you have any algorithm that can solve this problem, then this algorithm has exactly the same guarantees. So it's not up to constants or anything. It's just an absolute equivalence. Implication. Yeah. And okay, so why this is not done is exactly because of what Ilias is asking. That okay, we know the optimal algorithm, but these are high-dimensional problems. So the natural question is is this the best algorithm that people should be running in practice and everything? And the answer is not clear. And the reason is that this optimization problem, even if it's great and has all these great properties, it's actually potentially a computationally hard task. And this is where the complication starts in modern Bayesian parametric estimation. Okay, so now that I have all this abstract setting laid out, let's start with some more concrete examples of what I want to proceed. So I want to give you two examples. Okay, I'm not sure how this is going away. I want to give you two examples of where, the models of parametric estimation we're going to be discussing to give you an exact feeling about it. So something is, one model is what's known as a principal component analysis model, specifically the sparse tensor version that I'm going to explain. What is this Bayesian setting? So theta star for me is a binary k-sparse vector, so a uniform binary k-sparse vector. I want to learn this theta star. What type of observations I have now? What is this P of theta star? So it's the following thing. So now I lost the point. So I need two parameters to define the probability generating distribution. I need a lambda, which will be the signal to noise ratio, and P, which is the tensor. And basically, the data set that you have given theta star that you want to make observations, you want to make inference with, it's like the following form, is a P tensor. And the tensor decomposes in the following two ways. You assume the tensor is the summation of these two tensors here. The first part is a spike of this unknown parameter that is the rank 1 spike that points basically on the direction theta star, magnified by this signal to noise ratio, so amplified spike, plus just IID Gaussian noise per entry. So again, what is the setting? I'm giving you a T tensor that decomposes in the following thing. It has a signal somewhere, it points to a rank 1 in a rank 1 way, and it just has IID Gaussian noise per entry. And the question is, if I have this thing, basically, can I use it to infer theta star? So you see here in two dimensions, there is some direction that this is going to, right? And the question is can you find theta star given the data set? So that's why, there is a sparse tensor principal component in your data set. Make sense? That's one setting of interest. Now, of course, that's please.
I guess if T is equal to 1, this is a really easy problem.
That's a really easy problem.
Yeah.
Amazing. The difficulty starts when P is at least 2. If there was no sparsity, the difficulty starts when P is 3. Because, it's an eigenvector in P. Okay, but perhaps going a little bit slower, what is the best algorithm? That's perhaps a complicated scenario, but I told you there is a best algorithm. So, what is the best algorithm here? Well, you need to understand what's this posterior probability, but it's not hard because there's a Gaussian noise. So if you take, do the math a little bit with Bayes rule and, the Gaussian density, that is the best algorithm. The best optimization problem is the following. So you maximize overall potential values of this theta that you have here. and it's basically the objective value is basically the rank 1 spike of theta when it hits y, the tensor. And if that confuses you a little bit with any product, I mean the vectorized form of them. That's the optimal algorithm. Please.
How difficult this problem becomes computationally when theta star is not from this distribution, it's not random, but worst case.
Yeah, it's not the worst case will be with respect to y, right? Or you want about random y and worst case theta. Is that you see what I'm saying? There are two average case notions here.
Sure. But like if it wasn't the Bayesian set, that was a worst case vector that's sparse. How difficult is this?
This is, I would say, the same from at least this perspective, it's the same problem, the same difficulty. Like there is a reduction to the worst case theta star. Yeah, this is kind of if you want. Yeah, the worst theta star is the uniform one. Okay, but that's I guess goes in another direction. But yeah, okay. But coming back to the thing. This is the best algorithm, and what's the caveat? The caveat is that this thing, at least if it is at least 2, is an NP-hard problem. So like even if you have like the best algorithm, this case over the data set y, it's of course exponential points here discrete. Okay, but even if you forget the discreteness here with the sparsity constraint, and even if you forget the sparsity constraint, this non-convex optimization. So for multiple reasons, this is an NP-hard problem.
So it's not NP-hard for this random y, right?
NP-hard with the worst case y. So what does this mean? Is maybe there is an alternative algorithm that can match this, right? I mean, over random input, but in principle, it's an NP-hard problem. Okay. Right. So okay, that's one example. Let's see another example. High-dimensional regression falls into this scheme. So what is this model? I mean, again, let's say for simplistic binary case sparse signal. But now, what are the observations? There is some feature matrix X and some noise W, and you make n. Oh, maybe let me just make one comment to that here I forgot. As you increase lambda, this problem becomes easier, right? So like it magnifies the signal. So like, really here the question is, for which lambda is this possible? Like if lambda is 0, this is not here. Of course, you cannot infer it. If lambda is extremely large, of course you can, right? So there's a monotonicity in the signal to noise ratio. Okay, I forgot this comment. Okay, let's move on. High-dimensional regression. So there exists this matrix X here. So different probability generating mechanism. That you want to use to take observations with for theta star. There exists some measurement matrix X and some noise W with IID Gaussian entries, let's say, and you make observations of the following form. You hit theta star with this Xi and you add Gaussian noise to it. The more samples you have, the better it is. So here's the monotonicity in this problem, right? And okay, in vector form like this. And okay, it's the same problem. Find theta star from this thing. That's the Bayesian problem again. Okay, perfect. We know the story now, hopefully, right? The optimal algorithm is, you need to analyze this Bayes rule, the posterior, the Gaussian density, and of course it becomes least squares.
Ilya, just to clarify, it was a discussion before between the TCS and statistics. When you say optimal algorithm, you mean the objective that if I achieve to solve it, it gives me the minimum, some minimum error. Why you call it optimal?
Yeah, in the first slide I explained this, that like when I say optimal, I means that it achieves, if you want in your terms, the maximal probability of success.
Okay, great.
Or the minimal probability of error.
Great. So it is the objective, because by its own, it's not an algorithm.
Yeah.
It's the objective that if you achieve to solve it, yeah, fine.
Okay, I guess it goes into philosophical discussion what is an algorithm, I guess, but you're right. Yeah, I'm not telling you a way to find it. It's I tell you the optimization problem that if you solve, you're done. Good, yeah. Right. Again, what is the problem with this method? The optimization problem is that it's of course an NP-hard problem. Like under the sparsity constraint, with worst case y and x, this is not implying that there is an algorithm polynomial-time for this. Okay, so hopefully you get the idea. And really like these examples point to one question that I'm trying to point you to. The real question, I would say one of the, okay, I'm obviously biased, and I think it's one of the major questions in high-dimensional statistics nowadays. It's like, is there some time-efficient version of such story, right? I mean, of the maximum posterior estimator in particular. There are other versions, like you can discuss about posterior mean, but like similar stories. And, because it will have big implications, right? If there is some polynomial time alternative for this model. Okay, now, what's the news? The news are not great. In fact, a lot of researchers are now claiming or conjecturing, in fact, that the answer is no. In many cases. So like it seems to be that there is a phenomenon in many high-dimensional statistical problems, even very simple ones, like the one I just described, where we do have strong evidence that there are computational statistical barriers, as we say. So in other words, there are regimes where solving map would do it, but we don't believe there's a polynomial time alternative. Okay, that's called computational statistical gap. Let me explain in a figure. Imagine that this is the signal strength of the model, like this will be the lambda in the tensor PCA or the sample size in the regression. As you increase this thing, there is basically this following phenomenology. If the signal to noise ratio is super small, this is an impossible phase. Okay, so it's an impossible phase to find this parameter. But as you increase it, the following things happen. There is at some point that something is able to work. There is some algorithm, potential exponential time, that can do this, and that's solving map basically in exponential time, like that's enumeration, for example, with a discrete value. So this is the performance, the minimum lambda that map works. But then in many problems, actually, there's a complete order of magnitude for the signal to noise ratio so that we have polynomial time methods. And this is actually something we observe over and over in many problems, and that's called a computational statistical gap. Now, what type of problems exhibit this? I mean, there is regression problems, generalized linear models, periodical component analysis models, that the one I told you, covariance estimation problems, network models, community detection models. There's all types of phenomena, all types, I would say, of inference mechanisms that seem to be, versions of them seem to be exhibited. It's not exhibited by all models, right? There are models that, of course, you can do it, but there are many models that exhibit this phenomenon. And that's a very vibrant line of work that many people actually also here work on this. Ilias works on this, and many other people, Madison works on this. It's a very vibrant area, which perhaps the conclusion is we don't have perhaps the strongest evidence, but there is concrete evidence that this is an impossible regime for polynomial time, or at least conjectures that have evidence that this is happening. So this talk, though, even if, as Ilias mentioned in the beginning, I would say 50% of my work is at least on this, like trying to understand this hard regime here. This talk will not be about the hard regime. This talk will be actually about the easy regime. Okay, so what's going on in the polynomial time feasible regime? In this regime, there are algorithms, right? There are polynomial time algorithms for this problem. I will trust this as the rule, right? That this is the computational limit, okay? And then I will be asking what type of algorithms work here, which is then perhaps natural question will be like, okay, let's trust that this is the limit of polynomial time methods. Then it's natural to be asking what type of algorithms are actually working here. And, is there some common structure on this optimal polynomial time algorithm? Because remember, the goal here, you want the best time efficient alternative to map. So I think it's a very natural question to ask, what is the structure of this optimal polynomial time algorithm? So if you look at the literature of these problems, it essentially goes as follows. It's perhaps natural. A lot of times you just take the map and you do a convex relaxation, right? I mean, you convexify the constraints, and this turns out to be working, for example, down to what's predicted to be the limit. A lot of times you construct some spectral method. A lot of times you construct some message passing algorithm that's like belief propagation, if you ever heard of this, and stuff like this. Or a lot of times, and that's very common in this community, you approximate some statistic by a low-degree polynomial, and you should be saying, okay, this seems to be getting the trend. Now, there is some family of algorithms that if you have experience with the practice of statistics, is dissatisfyingly not there. And this is basically the class of Markov chain methods. So perhaps one of the most canonical ways of arguing about this problem from a practical point of view is actually to solve it with an MCMC method. And why is that? I mean, I'm going to explain, but the main reason is that it's an optimization problem, right? It's an optimization problem you cannot solve. So one of the most natural ways to attack to it is you construct an MCMC method that samples from this, and you run it for some time and you hope it works. Let me explain this more. So to solve map fast, one alternative, one natural algorithm is as follows. You choose a very large beta, and you tend the optimization problem, which remember is to maximize this objective over theta, and you turn it into a sampling problem, which basically says construct this probability measure. Okay, what is this probability measure? You choose a very large beta, and you assign to each theta mass which is proportional e to the beta of the objective value. Okay, so a moment of thought hopefully will persuade you that this measure for large beta is essentially supported on the maximizer. right? It's essentially like maximizing this thing. So one idea is you construct a Markov chain that has stationarity. This one, okay, it's irreducible and everything. So if you let it run for a long time, it will sample from this, so it will work. So the idea is maybe run it for not that long time, maybe for a reasonable amount of time, and hope it works. That's the whole idea of MCMC. Makes sense? So it's a very natural algorithmic scheme. And in fact, I claim that it's perhaps one of the most practical ways that somebody would approach this problem. Now, I'm a theoretician, so practice is one thing, but of course there is a question of, like how easy it is to be analyzed. And in fact, another attraction I find to this question is that in fact very complicated in some way. So like it's actually, as I mentioned, there is very little analysis of these models generally in high-dimensional statistics, and in particular for these simple models. They are very poorly understood how these algorithms are performing. And the reason is that, like, okay, the mathematical reason is that these are dynamical algorithms, and dynamical algorithms are very hard to analyze in random environments. And the reason, okay, again, maybe talking a little bit with you have your hands a little bit dirty in this area, is because you create dependencies across the iterations. So these are very hard to sort of usually deal with. So that's why in most cases we are actually, from the few cases we can analyze, we are good with lower bounds for this kind of models. We know a little bit of how to prove lower bounds, like failure of such Markov chains, but we know much less about positive results. Go for it.
So can you describe some cases where people use this in practice and we don't know how to analyze it, and indeed it gives you something good or something that appears to be good?
Yeah, we have to agree on a model, right? I mean, yeah. So I would say in regression, that's one of the most canonical ways to try to find the features. Like if you ask some statistician how you can find the features, of course you can run lasso, but they trust these Bayesian techniques even more. That's one canonical example in regression.
And they use it without an analysis?
No, I mean, well, it depends on the assumptions, but right. I mean, so there are worst case guarantees in some way, but if you try to test them and stress test them in these Gaussian models, they are really out. So somehow, like their projection into this theoretical literature, they're very bad. Yeah, that's the best way to state it. So yeah, so perhaps maybe I should say that there is this perspective of like we have these simple models as test beds, right? So then the question is like, can we understand at least in these simple Gaussian noise models what is the best algorithm, right? Of course, we don't believe reality is exactly this, right? But yeah, okay. So yeah, so that I think makes it an attractive direction from a theoretical perspective, right? There's something practical that's poorly understood. But perhaps when I got into this even more is that from the few results that exist, also the performance seems to be rather rich. Like in the sense that like it's not that we just don't know how to analyze them, but okay, we analyze a few cases and okay, they always work. No, it seems like that like the naive at least or the natural Markov chains, a lot of times they underperform compared to the best polynomial-time scheme. And that's something we do know from the 2020 in the analysis of tensor PCA, so some variant of the model I described you, but perhaps when I got interested in a community detection setting where we analyzed recently, where we realized plant peak. And before we tell you what we prove in this work, I want to give you just a feeling of what do I mean underperformance and rich structure in the way Markov chains perform. So I will give you some quick example of the tensor PCA. Okay, so what is tensor PCA? Well, I kind of already told you. So tensor PCA is this setting here. I mean, you observe the observations, which is basically lambda times a rank 1 spike plus Gaussian noise. Now, the literature I'm going to cite is only able to handle a spherical prior, so like a random on the sphere theta star. I know I understand this inconsistency with the discreteness of my talk, but it shows how hard this problem is. We do not know how to analyze even like on the hypercube what happens, but morally it should be, maybe okay. So allow me this inconsistency, it's the same intuitive picture. So you can imagine that's kind of a plus minus 1 theta star if you want in your mind. So, okay, so let's see what happens in this model. So what is the literature of this model? Makes sense. You want to understand for which lambda can you find this theta star. Okay, so what the previous theory tells you to do, well, I mean, if you want to run a Markov chain, that's the logarithm of the posterior, and you construct this measure, and you need to construct some Markov chain that has this stationarity. The most natural Markov chain on the sphere that has a specific stationarity is what's known as Langevin dynamics. You don't have to overthink about it if you don't know what it is. It's just some natural Markov chain that has the desired stationarity. So the most natural thing is to run Langevin dynamics or this Markov chain with this stationary measure and hope for the best. That's kind of the best, the most natural Markov chain you could be running in this problem. Okay, so let me tell you what we know. So perhaps that's the first thing I will use the board. But also to point you the picture. So the literature goes as follows. Like this simple model was defined by Richard and Montanari in 2014. So as you increase lambda, there is this following picture. The first threshold, the statistical limit, is when even maximizing the objective works. The best algorithm, the best method, if you want, works. So if lambda is around √10, we know below this, if lambda is less than √10, and asymptotically here hiding constants, we know that like the best method fails. There's nothing that you can do. The signal to noise ratio is very small, so you cannot find the parameter. But we have strong evidence that the best polynomial-time algorithms are working when lambda is less than another parameter, which is like basically n to a different power that scales with t. So like it's n to the t over 4. So that's kind of where the best algorithms start working. You need to be crossing this threshold. That's what we think, at least. And you can see, right, so if t is 2, of course, this matches this because that's an eigenvector problem. But if t is 3, this is where things start becoming order of magnitude different. And now you can see basically what happened is Gerard Benarous and Reza Ghessari and Okos Yaganath, basically 3 very strong probabilists. They analyzed the performance of Langevin dynamics for this model, and they actually got the following weird threshold that like the Langevin dynamics are working basically the moment you cross like this threshold. Okay, maybe I should say this was a tour de force using Spin-glass theory state of the results. It's a very complicated problem to analyze it. And it's using state of the art at the time methods. And right, that's the picture. Okay, so you do see already that this is rather structured, right? It's a different threshold. And perhaps it's disappointing, right? That's a bigger threshold. But there is some structure to this even more. And let me just say a weird identity. Somebody can actually see that there is some even more structure. So like for any t, like this threshold here is in fact the geometric average of these two. So like there is some weird, okay, it's a random observation, this one, but will be useful later in the talk. Like this, it fails in a very structured way. Like it requires a signal to noise ratio which predicts it in some weird pattern. Okay, random, you can forget about it if that bothers you. But the point is that like it fails in a very structured way. Okay, go for it.
So n to the t over 4, like
yeah.
you achieve this with like
a simple spectral method, in fact.
I see. So HSS has stored
Yeah, exactly. And there is okay, since you're asking, we know all types of lower bounds in this regime. Maybe I should have said, right? So it's we know, I don't know, like low degree lower bounds and some of squares lower bounds. I'm not sure there is an SQ equivalence. Yeah. So it's basically here something works. This is a hard regime. Something this becomes easy here, but it turns out that at least for this Langevin dynamics, that's a hard regime, and it becomes easy here. Okay, so hopefully you see there is some theory here which is non-trivial. Please.
I would like to clarify something about the Langevin dynamics.
Yeah.
While you run it, you sample more W's. Like
no.
you have.
That's the hard thing. If you were adding independent noise in each one, like SGD type of like, it's a much simpler analysis. Right. Yeah.
Wow.
Because you have less dependencies across iterations. Here you have one big dependency. Okay, maybe it's getting too technical.
I see.
Okay, yeah.
I was expecting that with multiple W's, the problem becomes harder because you hide the. Somehow, if you have one,
you have more noise. Yeah, but you can bring everything to lambda. But yeah, okay.
You cannot hide so much lambda anymore.
Yeah. It's a different threshold.
I see.
Okay, I guess I'm in a good point to actually tell you new results. Okay, so this is the story. Let me tell you what we do in this work. So we were motivated by all this whole direction, and we were like, okay, we basically offer a general user-friendly claim condition that if you prove for any discrete parametric estimation problem, you can immediately imply that the metropolis chain, a very natural Markov chain, run on the parameter space, will find in polynomial time the parameter. Okay, so we black boxed it in some way a little bit. So like we say, okay, Markov chains are hard. Let's say some sufficient condition that is general, that the moment you have it, you can at least claim immediately that like the metropolis chain is some with sampling from this measure I told you works in polynomial time. Make sense? That's the general, I would say, contribution. I will explain it in detail, obviously, in a bit. Used it in these two problems I mentioned, get positive results, right? So like we were able to get like some lambda that above this lambda you can find the sparse spike here, and some sample size that above the sample size metropolis works for the sparse regression. Perhaps interestingly, we prove that these are tight results. So because that's the next question, right? Like, okay, you found some Markov chain, can you improve the Markov chain? And at least in some generality, it's not every Markov chain, because every Markov chain is basically probably the whole P class or something. So like it's like, you know, some natural class of Markov chains, which are local. You can actually prove, including of course the metropolis, but much more than this, it doesn't work when our guarantees break. So like if lambda is less than this threshold, this class fails, and if n, the sample size is less than the threshold, this class fails. So in some way, you can argue we get this Markov chain, natural Markov chain threshold for these models by using this result. So these results are not very weak. That's what I'm trying to tell you, right? Okay. Yeah. Sorry if I'm bothering you with high level. Okay. And okay. But then there is a question of like, now that you have the results, where are they? Is this the picture again that they're failing, or are they actually getting the computational limit? And the answer is mixed. So in sparse PCA, it turns out that the natural Markov chains are still failing, like in tensor PCA. And actually, they fail gracefully, as I like to say. They fail in a structured way. They still satisfy the geometric rule. So you will see that like the same picture emerges, which I think it's puzzling but interesting. That like somehow like they have a predicted threshold, which is unfortunately not the computational one, but they're structured to this. But not in sparse regression. In sparse regression, it turns out that the natural Markov chains are getting the computational limit, which I do find also interesting. I don't have good reasons why that's happening, but it's happening. And then, okay, it's only a negative story, like such sparse PCA is actually Markov chains are underperforming. The answer is no, and that's the upcoming work actually that it's not yet posted with 3 students. We actually found a very careful way where we can remedy the Markov chain and go not in any way natural, but like not completely unnatural, but like not definitely in this class of natural Markov chains. Just a very careful hack. If you want, can create a Markov chain that I will explain a little bit that can do all the way to the computational limit in sparse tensor PCA. So somehow there is just, you have to think harder. That's what I'm saying. It's not kind of the immediate thing that you would do for Markov chains. And I think that shows how immature we are in defining Markov chains, I would claim, for these problems. And finally, I will not talk about proofs. I mean, it's already perhaps a heavy mathematical talk, but I would just want to mention a few things if you're interested to talk about this more. The positive result uses a technique in Markov chain theory that it's called canonical paths. It was introduced by Jerome and Sinclair in the 90s. It's an L2 contraction technique, if you have any familiarity with this topic. And for the negative result, we use a technique we introduced with David Gammaning during my PhD, and we call it overlap gap property in inference. It's a way to create bottlenecks for Markov chains. That's the high-level thing. I know if there are questions at the high level, perhaps in the rest of the talk, I will try to make things as concrete as I can. Okay? So let me tell you at least the positive result. So what's the general positive result for the metropolis process? In fact, it's a general positive result for any discrete optimization problem we care. So if until now you're like, I don't care about statistics, why I'm in this talk, then like hopefully this slide will be like, if you care about discrete optimization, I will tell you something interesting. Okay, so right, so okay, so what is the setting? Imagine that you want, right? That's the goal, right? You turn your optimization problem into a sampling problem by wanting to sample from exponential of beta times the objective. Okay, log of the objective doesn't matter, and you want to find a Markov chain that samples from this fast, right? Or at least, maybe let me rephrase to make it more concrete. Finds the optimizer fast using the Markov chain, like with this stationary distribution. Okay, MCMC methods a bit on 101. How do you do this, right? If I give you a stationary measure you really like, how do you construct an MCMC method that has a stationary distribution? It's a discrete domain. So the whole idea is you need to define some graph, right? The graph that the Markov chain will be using as a transition. Okay, let me write on the bottom here. So, okay, so what I'm saying here, like you have this exponentially large parameter space or feasible region in optimization, and you want to define a MCMC method, so you need to define some connected graph, right, on the parameter space. And if you have this locality, what Metropolis process is telling you, for any connected graph you define, if you put the Metropolis weights appropriately so that you have stationarity, the desired measure, that's it. Just run the Markov chain with these weights, and wait long enough, it mixes to this stationary measure. Okay? Hopefully you remember this thing from Markov chain. Now, the game is, of course, what is the graph, right? And that's the whole game. And just to give you an idea about the sparse binary cube, what is a natural graph, right, for support sizes in the sparse world? Well, perhaps I would say the most natural graph structure that somebody should be trying if they want to do local dynamics on sparse vectors is the swap graph. What's the swap graph? It's basically I connect two k-sparse vectors. You can imagine this would be the support of the vectors in more generality, if and only if they're one swap away. So if I have this feature and I don't have this feature, I swap them and I come here, and that's one step, right? That's kind of the most natural local changes that you can do in a support of size k, and keep it support of size k. So that will be the swap graph. That's one example of a graph you may be interested in. Perhaps I claim the most natural one. I'm happy if you have different opinions. Okay, so as an example, now what is our result? The result basically says if your graph has a specific property, then Metropolis works in polynomial time for any optimization problem on this discrete domain of interest, in particular for any discrete Bayesian estimation problem. Okay, what is the property? The property is the following. It basically says the following. So what we would like for the graph to have is the following property. Right, so okay. Like if this is your parameter space, somewhere in the parameter space, it is the optimizer, right? Where you want to go. Okay? You want to find this thing. So what we ask for this, remember that's an exponentially large space, right? So what we ask from this is basically the following property. What we want is for the graph to have a property. For any theta, for any other parameter, there exists a short path, like a polynomial path. Remember that's an exponential space. So a short path, a polynomial path, that has the property that as you go through the path from theta to theta map, it increases the objective. So what we need is just one path from any point to the optimizer, that across this path, this increases the objective. Equivalently, we want a spanning tree of this graph that has polynomial depth, and the root is the optimizer that always increases the objective as you go up. If you do have this structure, then we can guarantee that the Metropolis process on this graph for large beta will find this in polynomial time. That's the result. Yes.
So in NP completeness, for example, we say, look, if you have your verification, the verification path in your computation should be polylog in order to put it in NP.
Right.
Here you say something similar in the computational path, but you have more structure in the improvement. Do you see any connections of those two?
Yeah, I've been asked about this. I mean, I don't think so. Like, I understand the conceptual thing, obviously. I mean, it's I don't think so. Yeah. It's more like a result that we're saying, like, so Metropolis process for large beta turns out to be equivalent with randomized greedy for very large beta. So this applies for even smaller beta. So basically we're saying if you do randomized greedy on this graph and there is one direction of improvement, then basically the randomized greedy will eventually find it. That's one way to put it differently.
And is it strictly increasing or just
sticky, and that has implication the runtime. Now there are variants you can prove that actually we never use the actual result, we use variants of the result, and that's the nice thing about this result, somewhat robust to variants. Even if you have on the subset of the graph this property, like as long as you can prove that the Markov chain starting from the subset of the graph never leaves, it still applies. These are very useful variants, or you can prove if it's monotonically increasing strictly on a subset. There are variants, but that's the moral. That's the moral. Yeah. Okay, so having this result into game, the whole idea is like choose a graph and prove this property. I'm not saying it's an easy thing to prove this property, right? But at least you don't have to think about Markov chains. We did the Markov chain part for you, like of why like the local dynamics will work. Does it make sense? Okay, so basically what we do is you apply this in sparse tensor PCA, we got the following result.
Yeah. There's some easy way to see why this property holds for that next problem.
For the sparse tensor PCA, you say?
For example. I can't see.
Yeah, it's not an easy problem. It's not an easy problem, but it's not a hard problem as well. So you have to somehow, union bound a little bit over, like prove that you need to construct this tree. So you need to construct this tree and prove with high probability because there is randomness on the data. Like, so if it's a worst case data, still, I guess you need to construct the tree, but to prove existence, it's deterministic, I guess. It's right. You need to check the spanning trees. But for the probabilistic way, what we do is we prove that basically for any point, I can always find another point that has a higher value that somehow goes and it constructs a path. So basically, we construct the paths individually when we merge them. It's actually not. Yeah, there's combinatorics involved, but it's not. Yeah.
I suppose if you're just looking at a small case, you could see how it could happen.
Yeah, exactly. For small cases, you can do this by eye. But I think it's a good. What you're asking is a good question. Like, can you automate this, for example, like for I would say even for random data? Like, I think that's a nice algorithm question. I haven't thought about it.
Yeah, there's a question in the Zoom chat. If they have this property, then is MCMC the most efficient way to find that solution?
That's a very good question. So, okay, I'm not sure where this person is coming from, like, because there is a very similar question. That's a very good question. So I will try to address this potentially what they mean. So, like, there is this following argument that somebody can make. If you have this property on this graph, why don't you run just the greedy method? So with the greedy method, it's something like just choose the best neighbor you have, and in terms of the objective value. So like, you are here, choose your neighborhood with the highest value, and somehow you can prove that like you have at least some improvement per iteration, and somehow there is some argument like this. The thing is that relates with my argument that we use variants of this to actually conclude our results. So like this greedy type of algorithms, the moment you break some of these assumptions, like you only have for a subset of the graph to have this property, it just completely fail. So somehow it's extremely crucial, the randomized aspect of the MCMC method to use it, in fact. Like, because it's more robust to small changes of this model. That's my argument, but it's a very, very good question. Yeah. Okay. Okay, so how we apply this for sparse tensor PCA, let's come back to this model. Again, spike, lambda plus noise, binary case sparse vector, and the sparsity, let's say it's P to some power. Okay, so what is the phase diagram of the literature, and then how do we compare? Similar story, like you increase lambda. If you just analyze the performance of the optimization problem and you just do brute force search, the minimum lambda that is becoming possible is what's known is the information theory limits around root k. This is where map works, and some very involved recent paper, or now more not that recent, I guess, but very nice paper analyzed using known conjectures for what's the computational limit and derive this complicated formula. I'm not going to rewrite, but it's a complicated formula. We do believe it's the limit of polynomial-time methods. Easy. And then we'll be like, okay, where is Markov chains in this? Okay, but maybe I should say for any t there is a gap. For any t there is a hard region, like even t equal 2, sorry. For any t at least 2, there is a trade-off. And basically what we do is we say, okay, great, that's the setting. Now run Markov chains. Consider any Markov chain that has this stationarity, the desired stationarity, and you operate on the neighborhood graph, which is the swap graph. Okay, so like you fix the graph. That's the swap graph, which is the natural sparse neighborhood structure, and try to understand how Markov chains perform in the swap graph. So basically, informally, the result goes as follows. We prove that like some Markov chain with this stationarity finds in polynomial time the parameter, if and only if the metropolis weights on the swap graph finds the parameter in polynomial time, and if and only if this lambda is bigger than this weird new function. So what do we do? We say basically, we analyze the metropolis, the positive result, with the result I just told you. We prove that if lambda is large enough, whatever large enough means, then there is this short increasing paths in the swap structure. That's the positive result with high probability. And if lambda is less than this thing, all Markov chains will fail on the swap graph. Okay. Now, hopefully you don't spend too much time thinking about what is this threshold and stuff, but you actually, okay, because I don't want you to overfit on this. The point is that like for any t, this is bigger than this. So actually for all parameter values, there is a Markov chain underperformance. And perhaps what I find somewhat striking is that for any t and for any k, they fail gracefully in the sense, in a very structured way. Like, again, it's actually somewhat really striking, right? For any parameter regime, k to the t minus half and root k, if you multiply them, you get basically like the power 2 of k to the t over 2. So it's a very structured thing.
So do you have an explanation?
I don't. That's one of the biggest questions I have.
They are weaker than
Why they're weaker? Also, I don't have an explanation for this. Yeah.
They don't match what other algorithms.
It's very surprising because it's you would say that this is more involved by simple spectral methods. I don't. Actually, in sparse regression, the same story matches it. So there's something in this Gaussian additive structures that fails. I don't have a good interpretation at the moment.
So for PCA, for like matrices, you're fine, right?
No, equal to also includes this. Sparse for sparse. If you give me a dense one, yes. For dense, it doesn't make sense. Yeah, under the sparse there is still a gap. Okay, sad story, but it is what it is. So like for t equal to and k to the less than root p, basically the threshold looks as follows: root k to the 3/2, k to the 3/2 of Markov chain work. Of course, this is the geometric mean of these two. And it's absolutely, because t is 2, you can even matrix case, you can even run some experiments. Of course, these are not the most proficient plot you will see in your life. But, like that's more or less what's happening, verifying the theorem. So even if you have 3,000 features and sparsity 15, you do see if lambda is k to some exponent, and this is the number of iterations, if the exponent is less than 1.5, you take more than 1 million iterations for the metropolis to find the parameter, and there's a sudden drop, essentially, with some fluctuations above 3/2. So it's a real threshold. I mean, it doesn't need p to be like at least 3 billions or something for it to kick in. Okay, now let me quickly tell you a way to fix it, to make it a little bit of a lighter thing. So there is a way to fix it. There is a way to define a better Markov chain. But yeah, it's not anymore what I will be satisfied with as here is a natural Markov chain, that's the natural thing to define. It really leverages the structure of the model. So what is the Markov chain? The Markov chain is inspired by some recent work on what's known as the plan-to-click problem that does the following things. First, it doesn't operate on binary k-sparse vectors. It doesn't operate on supports, if you want. It operates on all subsets of the features. So that's the whole binary cube. That's the first bizarre thing to do from a statistical point of view. You don't care about your sparsity requirement on the feasible region, on the state space. But perhaps naturally from an optimization point of view, you regularize it. You impose on the objective the sparsity. Of course, you would be like, that's very natural in an optimization point of view, but it's, perhaps unnatural, like from a direct statistical point of view, it's kind of, why would you do this in the first place? But if you do this, mathematically, what do I mean is like, you take a metropolis process that samples from this measure. Okay, so that's the same log likelihood here on the binary cube, but then you add some function of the sparsity, like, to penalize it, to go down. But it turns out that actually what I find particularly surprising is that you need a very, very specific choice of gamma and exponent here to make this work. Like an extremely tailored, that I don't understand, kind of regularizer that you can do this.
Graph is still the SWAC graph?
Yes. No. Sorry, what I'm saying, like it's not the k-sparse vector, so there's not a swap graph. You go on the you go on the exactly in the hypercube, Yeah. I think it's natural. Let's say yeah.
So there are easier paths here, I guess. This expansion somehow.
Yeah, but more. So somehow the union bound makes it. Yeah. So you see what I'm saying? Yeah. So it's more entropy. Yeah. But so more points. Yeah, more points, not more paths. The paths are good. More points. Yeah. Okay, but what I'm trying to say here is the result. Again, I'm not giving every detail because that's not uploaded yet, but I'm giving some detail. It's a complicated even statement, but more or less the statement says if you have a sufficiently warm stat for initialization, it doesn't work for any initialization. You need sufficiently angular distance, small angular spherical distance to theta star. Don't overthink this. Then if you have metropolis there, it will work down to the computational limit. So yeah, maybe I didn't say here. The previous Markov chains had like a different transition, right? And basically we're saying that like you can get down to here with this algorithm. Now, can you find such a warm initialization? That's the next step. And it turns out you can, in fact. Like there is some way to do it uninformative even, without looking at the data, just checking polynomially many initializations. There is some way, it's not immediate though, there is not one initialization that can do this. Like there is some way that you can initialize this process, but you need to think how to do this. That's the result. Let me perhaps say just one intuition, mathematical intuition, what fundamentally changed without giving a lot of details, as I said, but like still hopefully conveying something. There is something that fundamentally changed here, right? So why do you even consider the binary cube? Okay, and perhaps the best way to explain this.
Sorry.
Yeah, tell me.
In MCMC, I understand. So your initial distribution is just a Dirac distribution over a very specific theta. I was lost a little bit.
You mean the result of this one? In that result, you can choose. I'm telling you, condition on the initialization, the following things holds. If the initialization have this property, you're done, and then the question is, can you enter this region? Yeah, that's what I'm saying. That's the second thing.
Okay.
There is some polynomial-time algorithm, actually a brute force polynomial-time. That's second polynomial. You initialize polynomial many times. That's what I'm saying. But I'm not sure which one will work. It changes with the randomness. It's not that
best iterate.
It's a best iterate. Yeah. It's I told you it's involved. It's not a super involved algorithm. It's involved from the mindset some simple metropolis process should be working, right? Okay, but I want to give you some intuition of at least the way when I was convinced that something like this should be okay. Yeah.
One last question. Typically, when you learn MCMC, you learn also the Ilias simulation annealing, that you are changing the temperature better. Here, you don't do it at all.
I don't do it at all.
You never said that you can change it.
I'm not changing beta. So, okay, there are two answers to this. First, I don't know how to analyze the changing beta. That's the honest answer. But a lot of but here is a kind of, a perhaps more mathematically sophisticated answer. A lot of the lower bounds apply for a very high range of betas.
I see.
So we can prove lower bounds against simulated annealing as well. So like in most of these cases that I mentioned, like you can prove for fixed beta it works, and for at least in some range of betas failure, but there is still room. So like somebody can argue, no, but you don't start for low enough beta, and that we don't know.
And maybe the low enough beta gives you a very good initialization.
Yeah. Actually, that's. I mean, I had many arguments with physicists about it. It's a.
What physicists believe?
I would say at the end. Okay, so yeah, so it's okay, but yeah, okay, let me just give you actually I don't know how much time I have, so yeah. Okay. Okay, sounds good. Okay, I continue, but stop me. Okay. Right, okay, so let me just give you a very quick intuition of why this result, this lifting, as we say, or over parameterization, it depends how you say it, like actually works. The reason is that the moment you go to the cube, you can come closer to theta star. That's more or less the intuition. So, okay, let me explain this. So let's say your goal suddenly is to initialize close enough from theta star to theta star. That's your goal. So your goal is the following. I want to maximize over theta 0 like the angle I have with theta star. Okay, so what would you do? One idea is, okay, just stick to the what theta star it's a uniform K sparse vector, like K sparse binary vector. Now, one idea is, okay, just produce your best guess. So your best guess is choose theta 0, which is not uniform, which is binary and K sparse, right? Just start with this, somewhere on the parameter you are. If you do this, what is the angle, right? So the angle is very simple, is probabilistically. The angle you will get, because it's a uniform one, it's basically, okay, with a small amount of math, it follows the following distribution. It's what's known as an hypergeometric distribution with these parameters, divide by k. Okay, maybe trust me on this. And that means that approximately, just from the concentration of the hypergeometric distribution, it has angle like this. Like the best angle you can get, it scales like this quantity. Basically, the thing is, the moment you go to binary vectors, not just K sparse, you can go to the root of this angle. You can come closer in the sphere, uninformatively. So, like, there is a way using binary vectors just because of the geometry of the cube to come closer. Like the root of a number less than 1 is bigger than the number. And somehow, like, the best way to see this is as follows, right? So if theta star, let's say somebody initializes from the only one vector, which is not K sparse, then what is the angle you will get? So the angle you will get okay, the numerator is the only one vector hitting a K sparse vector, so it's just K. And just compute the norms, you get basically root P times root K. So root K over P. Right? So basically you get, like, just with the only one vector, you get a sufficiently better performance. It just so happens that somehow lifting makes you come initialize closer, which is counterintuitive in some way, right? Why would you lift? Yeah, perhaps it's counterintuitive. It depends how you see it. And perhaps it's intuitive because you get more points. But yeah. But right. So the point is that somehow local methods are very sensitive to initialization. So if you initialize close enough, you have a higher drift. And you may be thinking, okay, but how do you think to lift to the binary vectors and not to something else? And there is just one more calculation I want to show you that, like, it's clean. It's clean. It gives you some more clean intuition about what's happening here. So the reason you would go to the binary vectors is the following thing. Let's say you simplify the problem, and your problem now becomes you now believe me and you trust me that the whole game is to initialize close with the unknown vector. So you're asking the question, what's the way to minimize your expected distance from theta star, from the unknown theta star in the mean square error sense. Let's say that this is your goal, with no data, just to come as close as possible. Then who can tell me what's the minimizer of this mean square error? If I don't give you any information, like about this problem, like which A is as close as possible to this random vector. Okay, I don't want to test you in any way. This is just to give you something to think. The optimizer is always to take the mean of this vector, but by bias variance decomposition. So they always optimize the single vector that you should be choosing to come close to the random vector. To a random vector is always the mean of this, right? Because this is just the variance, like, of theta star plus the bias, right? So you just make this 0, right? That's the minimizer. So the window of this random vector is what, right? That's a symmetric distribution across coordinates. So it's just proportional to the only one vector. So basically, like this simple calculation tells you that if you want to come as close as possible to a binary k-sparse vector, you should be using the only one vector, which is not k-sparse. That's kind of, more or less, okay, hopefully my intuition at least, hopefully it means something to you, what I just did. Okay, right, so let me conclude perhaps. I had one slide for Gaussian sparse regression, but I don't want to go too much over time. Perhaps just the implication is, what I want to say is the following. This is a completely different story. Things work great here. So in sparse regression, if you just do minimize the least square with the metropolis process or the swap graph, things just work down to the computational limit, which is, the computational limit is achieved by Lasso, if you're familiar, and it's achieved also by the metropolis process.
But you didn't apply regularization here.
No, that's what I'm saying. Everything works perfect. I mean, it's like the most natural, there is no magic you can do. It's the natural thing. Of course, you need to prove it, but it's the short increasing paths exist, like down to the computational threshold. Please.
Assumption on what x?
Yes, very good. This is in the simple case where x is just IID Gaussian or with a covariance matrix which is very well regularized. Yeah.
And so that would show up the same way as
actually restrict isometry property or restrict eigenvalue. Yeah, go for it. So yeah, that's enough. That's enough. And that's because you need to construct these paths. Yeah.
So there's nothing beyond what we know.
No. Unfortunately, yeah. Perhaps an implication of this works here is that you cannot beat what we know with polynomial. But with this is good evidence that the current state of the art is for compressed sensing is optimal.
A high-level question. Maybe you said it, but is there a way? Do you know when you can stop your chain? Is that coming out of your work?
Right. So this is very good question. So our guarantees are more like of the form if the time is that large, stop, and you're okay. It's not stop and then do a final test. Right. So you cannot test this besides.
Could that be done? Do you think? Is that something that's possible?
Yeah. Because if you're close enough. This is testable. Yeah. Like the least squares error will say it's that small. Yeah, you can predict the value. That's what I believe. Yeah. Makes sense. Like you made the error so small. There is a level set of the error that if it's reached, I think there is a converse implication that you are done. Yeah.
I get, that if you have X and you know that theta is binary like that, then I could know how big that error level is. But in a real problem where theta isn't, we don't know how big theta is.
Yeah, then you don't. Yeah, you don't. Yeah, absolutely. No, you're right. It's an artifact of this planted kind of or ground truth perspective. You're absolutely right. Yeah. Okay, let me conclude. Okay, this was the results again. Okay, what are kind of some future questions that I think are natural here? Well, I mean, there is a mathematical question I like. That's, of course, is a little bit esoteric. But I don't understand why there is such a structure in the failure of Markov chains. Like, why is there a geometric rule appearing in this signal-to-noise ratios? I think I have some calculations, which is a little bit heuristic. I haven't written down anywhere that like actually will generalize for a large class of models that look like this. But I'm not sure what's happening. It's definitely not true for sparse regression. I'm not sure. A more algorithmic way, algorithmic problem that I think is natural here is how do you remedy Markov chains? I mean, okay, you can of course lift, do a bunch of tricks. Like, it would be much nicer if there is like a canonical way, right? Because you cannot go into, for example, a person that is interested in these algorithms, let's say in a more practical perspective, and tell them, oh yeah, try to lift. I'm like, how can I lift? Like, okay, so it's a lifting means lift the constraints from the parameter space. Why I will lift? Okay, lifting in Markov chain theory usually means extend your state space. That's what formally it means. Here we used it by going from k-sparse to not sparse. And you put a different regularizer or something like this. It's not lifting on Markov chains, but of course you can, I don't know, call it over parameterization if you want or something. Okay, and I think the argument with physicists is something what Manolis was saying, that maybe just simulate annealing would do it. Like just start with a very, very low value of beta and start basically increasing beta. It's another whole layer of mathematical analysis here, which I'm not sure how to do. But I don't know. Yeah, it's an open problem, of course. Maybe that would be it, maybe not. Perhaps a relevant thing that I want finally to mention is that like there's some recent work on analyzing global dynamics like metropolis process in perhaps a simple case on principal component analysis model that I mentioned, but under no sparsity on tensor constraints. That's the matrix PCA that basically is able to prove that in this case, the metropolis process or the global dynamics work down to the computational limit. Just the most simple PCA model you can imagine, no sparsity on tensor structure. But interestingly, what I was saying, this work, they use some stochastic localization techniques. That's an interesting new mathematical ideas in the probabilistic literature. And I think it would be very interesting to see if they have any power in sparse tensor regimes, because they do apply for lower values of beta than what we analyze here. So there is a chance that this could be a way to analyze simulated annealing, for example, or something like this. Okay, that's more or less what I want to say. Thank you very much. Yes.
Say here, like the genetic was fundamental for Gaussian additive models, but you said like it didn't show up for the regression, but didn't in the regression you put like Gaussian noise into the data in the first place?
I do. So somehow in regression there is some extra layer that you multiply your signal with something. There is. And by the way, I don't have a theorem like this. That's just a question, right? Yeah. But it definitely doesn't contradict this. This is a very simple. In some way, you could be like, that's a very simple model, right? You add to your signal noise, but it's not a signal. It's a function of the signal. It could be the tensor structure or something like this, right? Yeah. But it doesn't have extra randomness, like in the regression.
From the speaker again.